Good morning. I know we have a little bit of extra time today. We're happy to see you. I teach part-time, and I tend to ramble. Charlie teaches as well. So Charlie, if you could join. So, first of all, Charlie Kamara works for NASA, and he's an astronaut. He's actually been in space. His job at NASA is right now largely around innovation, and he is passionate about this topic, and we've had lots of discussions over the years as to how we change the way we do education in this country. And so one of the things that we did at NYU is to build a platform that lets us turn the model of education upside down, which is, rather than it being top-down and outward-bound delivery, it's more of a collaborative experience that allows people to build and share and curate their lessons. And we still call them lessons. I mean, you might find a better word at some point, but and do it in a much more granular way. So a lot of what we did was we built a platform around WSO2. We used another tool called LifeRay, and we built a very social, collaborative environment. We're partnering with NASA. We just signed a Space Act agreement with NASA to help build content and share content across NYU and NASA. And so, we're really trying to innovate around this area. One of the fundamental things that we have to do is reduce the cost of change. And that's one of the problems that I've encountered both at NYU and my previous experiences at the New York Stock Exchange, where I spent almost 10 years, and in the defense world where I helped build diagnostic systems for F-18s. Very rigid environments that required lots of effort to change things. And I was telling somebody last night that it took about 6 months to get a single line of code from inception to delivery to the fleet when I was building stuff for the F-18. You have to go through so many layers of reviews. It was insanity. I can tell you the financial world was not that much better. And I know a lot of people were probably shocked and surprised. Let me get into the presentation, and we'll talk a little bit about what we've done and where we're going with it. All right. We're going to do a clicker, right? Let's see. Bear with me for a second. Your wife can use it. All right. So now I can see what I'm talking about here, and I have to keep turning around. So this is Charlie's bio. Born and raised in Queens, went to Poly, was the chief engineer at Johnson Space Center, and flew on the return to flight mission after the Columbia disaster over Texas. Was passionate about the problems that occurred there, and one of the things that he did with a couple of other astronauts is they found a solution for how to replace tiles in space, which was going to be a long, multi-year project done the traditional way. They went into a garage. And so the motto, I think, was fail quickly, fail often, and do it experientially rather than going through the long-winded process where you define, you build, you test, and then 2 years later you say, that didn't work, let's try again, right? So this is what Charlie was instrumental in doing when he went on the STS-114. All right. This is me. I already described who I am and what I do. I work for NYU, largely around educational innovation technologies. And so when we talk about agility, what is agility, right? Agility is the ability to do something with speed and accuracy, right? So one of the problems with speed and accuracy is if you carry baggage, it's going to reduce both speed and accuracy. You have to insert a lot more force to make it accurate, right? So the bigger your payload, if you will, the harder it is to make it very precise. So one of the guiding principles around Agile is lean principles, which is get rid of the stuff that doesn't matter, and make a lot more smaller iterations that allow you to correct in course, not correct at the end of the course, right? That's the big problem. Is the way most people build systems is they correct at the end. So we decided to do this Agile process at NYU. Where I am at NYU right now is in 10%, which is new innovations. There's improvements take the vast amount of our resources, and then some enhancements, but the edge stuff is what you'll probably see here today. And we're in the third beta of a project that we started about 6 months ago. And Charlie's loading some of his content into that platform now. And I have to make sure I reserve enough time to let him show you what he's doing and what he's, because that's a lot more interesting than what I'm going to show you. So this is the traditional Agile process, which is sprint-driven. There's no long, winded, kind of development cycles, and everything's done. And we do 2-week sprints. And at the end of each sprint, we look at what we did, we look at our backlog, see what we consumed, and adjust our velocity and continue, building. So we built this system in 6 months. And I can tell you, if I did this in the commercial world with a traditional model, it would be multi-year, multi-millions of dollars. So we did this in about a quarter of the time for less than a quarter of the cost of what it would have taken to do it the traditional way. I'm not going to go into the Agile Manifesto. The slides will come to you, and I think there's some interesting things here, but in the essence of time, I'm not going to talk about it at the moment.
Take your time. Take your time.
All right. I want to give you enough time.
No. You take
Normally we bicker a little bit, so you might see a little bit of that. All right, so guiding principles for us: start small, small concepts. Sometimes we do them kind of in a stealth manner. You don't want the parades out there announcing that you're going to go do this big thing, because that will create all kinds of pressure to, build risk reduction into your plan, and that makes it heavier and harder to implement. So the other thing is we balance risk and value. So we look at both risk and value and prioritize the sprints accordingly to maximize the amount of value we're delivering and risk reduction along the way. So when we go through this initial exercise to figure out where we are in terms of requirements of what we're trying to build, we look at in a very quantitative way, where is the risk and where's the value. And I'll show you a little bit of that. First implementations are always going to be flawed. Good enough will get better. Perfection will never arrive. So if you're being pushed to be perfect on the first cut, you're probably going to fail. It's a really so I think the ability to fail safely, and I think Charlie will attest to this, is an important part of the culture that you have to have. Is can you build something in a way that gives the value early, and then when you have that value, then you invest in bulletproofing and adding all the other layers. And a lot of times the innovation comes from a combination of things. So we built all of this on top of the WSO2 Enterprise Service Bus. We're also using a portal platform called LifeRay, which gives us a kind of a collaboration social platform that layers on top of it. Everything is modular, and this is by virtue of the architecture, the reference architecture that we chose, so that when we plug in a new component, it doesn't have all these embedded dependencies on everything else. Everything is kind of uniformly removable. So we can add new features, we can upgrade new features in flight. We don't have to bring the system down recompile, relaunch the whole thing. We can do it modularly, one piece at a time, which is huge. And when we started the proof of concept about a year ago, we got enough support that there's 3 projects going on in NYU now to embrace the technologies. I'll talk about that a little bit. So the challenges for us were, around hardware. How do we provision servers and networks faster? The old way is slow and very difficult to do, so that was a big drag on innovation for us. New features and how we integrate them into the current platform, and how we improve the user experience and make it more social and collaborative. So we have 3 projects running right now addressing a lot of that. We decided we're moving towards a hybrid cloud, and so we're going to actually have a conversation later on today and talk about how we can build. Right now we're in Amazon, so both WSO2 and Micro are running out of Amazon, so we were able to roll things out very quickly that way. We're now challenged by the opportunity to build this on-premise. And there's a lot of reasons why you want to do that, not necessarily cost. And there's a lot of debate about cost, but it's more about data. And in the computational world, you have to be very aware of what data is where and how you can let that out. And I have a personal opinion that Amazon and the public cloud is relatively safe, as safe as your service and your data center. And people have a mistaken perception that it's imbalanced that way. They have Amazon has a lot more resources and a lot more at stake in protecting their environment. You have to protect your service no matter what, no matter where you put them. If you put servers up on Amazon, you got to protect them the same way you would protect them in your data center. And in fact, in some ways, they're better protected in the cloud because of the way they build and launch stuff. Everything is turned off by default. But if you're building servers yourself, a lot of stuff is opened up and you have to go through the process of shutting things down, closing ports and stuff like that. We want to do dynamic service provisioning, both in the private and public cloud, and dynamic load balancing, all huge. We have 3 new campuses, 3 campuses, major campuses around the world with 12 portals. All of them are connected, and all of them share a lot of the same information. So being able to dynamically load balance at a distance is a challenge for us. And in some ways, and I'm actually going to talk about this today with some other folks about how we can do that through WSO2 and move towards something that I call an enterprise service fabric, which is multiple nodes of service buses connected at a distance, all talking to each other, all synchronizing. You get local latencies no matter where you are. If I'm in China and I'm connected to some application there, I'm getting local latencies. If I come back to New York, all the data gets replicated, and you can interact with the nodes in New York, and everything stays synchronized. That's the idea. Who knows when that'll happen, but that's what we want to move to. So this is our reference architecture, if you will. Right now we're using service bus, data services, and APIs, the API module. Moving forward, we want to use complex event processor and business activity monitor to do a much more integrated way of monitoring and alerting, including security. We're going to treat security as another health status of the system. So if we see a particular node change behaviors, and we know that it's supposed to be a web server and it's scanning ports, that's not a good thing. So that's the direction we want to move in terms of our architecture, being able to detect those things live and be able to respond to that live. I think we talked a little bit about this already, and I'm trying to preserve enough time so Charlie gets to talk about it. All right. Oh yeah, we started a little early, so we have extra time. So we're using the traditional patterns through the service bus, and using the guaranteed message delivery. We're using filtered as a mediator. And so there's some really interesting publish subscribe is huge. And that's I guess the primary method we use to access data. And what that does, interestingly, is when you have an application that needs to access more data, you don't have to change the APIs and the method signatures and all that. You can do that by changing the what the level of access that application has. So you can change one module and can consume more data, and you didn't have to change anything else. If it was already published somewhere else, it's available to you. So that's a really interesting idea about how you increase agility. It limits the scope of change radically when you start to think about software in that way. And I can go through all the other methods that we're using. So we're going to switch tracks a little bit and start talking about the case study. So what we call the platform is the NYU Knowledge Commons. And we looked at the kinds of things that we wanted to do and looked at the risk associated with it and the value that it provided, and that gave us a way of prioritizing our work. Number one for us, and there's a really good reason, it might not be apparent initially, but we wanted to improve the way we deal with the granularity of data. So if you have video, if you have PDFs, you have PowerPoint or what have you, normally you treat that as a kind of a black box that you include on, and that's kind of the YouTube model, right? What we've done is we pushed everything through a transaction service. We extract metadata from that, and we do a chunking exercise to help build addressable components of let's say, a video. So now all of this becomes accessible to the author and to anyone they share with. And so one of the ideas behind the platform is to create a layered collaborative approach and be able to reuse that content. Not the whole big black box of video, but portions of it. And you can weave them into a different story and collect them. And so the idea here is not to create a learning management system. It's to build a collaboration system for authors, and it could be faculty, it could be students, it could be researchers, to layer and reuse and repurpose information, and then create dialogues around that, social dialogues that give you crowdsourcing feedback that says, I like this, I don't like this. And then when you have something worthwhile, not even push that into an LMS or into a classroom vehicle. And one of the things that we're looking at for the classroom is really three principles, which is you don't want to treat all your students the same way. They're going to have different needs. Brick and mortar sort of drives you to teach the same way to everyone, and you don't get enough feedback to really be able to differentiate. A digital approach has a lot better opportunity to do that. The second is you don't want to time box the student into having to learn this in this amount of time. They can do that on their own time and to their needs. So you might have layers that you don't necessarily have to go down the path of if you already know that material. So you can be much more adaptive in how you deliver content to students, whether it's fully online or in a hybrid mode. And the third is you want to correct misunderstandings or early, right? So you want lots of feedback. So when you present a concept, you want to get that feedback right away before that seed becomes a sprout, right? So you want to get them once, and very often when I teach, I don't really know how well the class is doing until the midterm, and that's not a good thing. So I'd rather know that day, can we, fix a misconception early? And that's one of the things that we're looking to build into. So we decided to add all of these different things, including a digital asset management system, user experience, collaboration, and so on. This gives us kind of a roadmap on how to implement the system. And then now we can go into a case study. This is what the system looks like right now. I can give you a live version, but I think it would be better to let Charlie talk a little bit about the kinds of things that he's doing with collaboration and innovation at NASA, And at the end of that, he'll show you the kinds of things that he's done in our
And
platform.
you could talk about it. Yeah.
Okay.
Yeah.
Cool.
Yeah, that'll work.
All right.
And Peter's the genius, so he's going to get me to my slides. And it's interesting, how many people here are mechanical engineers or aerospace engineers or nobody, right? And so you speak in tongues to me just like Peter does, but he's a very, very sharp person, and I trust everything he says. But if I can learn his language, okay, I can see areas where the code developers are agile and they're effective and they work together and globally in a flat environment, almost leaderless type environment, and getting amazing things done. Wow, wouldn't it be great if I could get engineers to do that, right? And so there are analogies that you could make from this, just like stuff I am saying to you, you might not quite comprehend. So, or you will comprehend it, but it will sink in and it might relate to something you're familiar with. Okay, how did I get into this? I flew right after this accident. A large piece of foam came off the tank, hit the wing, and really smart people on the ground made all the wrong decisions. They thought they knew something they didn't know. Okay, and that's a failure that we have. But more importantly, I was training in Russia when this happened. I knew nothing about it. This was on launch that this happened. Otherwise, I would have flown home and beat down the door and probably got reassigned again. Because this was a big problem. They did not go outside their little safe private Idaho and Johnson Space Flight Center to ask for help. Wouldn't it have been great if we could have connected with people around the world that actually knew and could give you real data that said, you know what, this is a problem. That foam striking that wing can cause damage. Okay? Well, they made the wrong decision, and that was the outcome. We lost 7 people, 14, 16 days later. Okay? Then what is not going to show here is what they did at the end of this, after we lost the crew. They wanted to prove to the world that, hey, that big piece of foam could do something. So what did they do? They made this tremendously large test with a large piece of foam hitting almost a full-scale replica of the wing. A $10 million test, what I call a dumb, slow, stupid, late test with very little data. That's why it was unintelligent. And they blew a gigantic piece of box-sized hole in the wall. And they said, see, that's what caused the accident. If we would have let them do that, they would have been an unintelligent, would have been a stupid test. Okay, what you're not going to see, you are going to see it, is we said, wait a minute. We told the Columbia Accident Investigation Board, wait a minute. We have really good people at research centers that come from a different culture that know how to solve this problem. In 3 months' time, before they ran the test, they had a solution analytically that almost exactly predicted the failure. Imagine if we had those tools while the crew was in orbit, and we could say, wait a minute, flight directors, there's a problem here. We have a problem. We need to do something about this. We could do this, and that's what I have a passion for right now. I'm going to be going very fast, almost like a Disney movie. If you go to, the flip book kind, where the little characters move, if you go to Vimeo, Google my name. I gave a presentation like this at Siemens about a month ago. I'm a lot more coherent on that presentation. You'll be able to run it over and over again. But this is what I call a failure of imagination. We could have made major strides in motivation, education, and how we solve these problems. Have really bright people doing it, but they're not using the right side of their brain. They're not being creative. Chris talked about our kids. Well, this was me training in Russia, okay? Very old, stodgy, pedagogical style of a person. That's why I don't play cards. That's why I don't play poker. That's what our kids look like when we're trying to teach them using the techniques we're using today. If I had a gun, I would have blown my brains out. We can make advances in each of these areas. We're doing problem-based learning, getting the kids involved in real epic challenges. Why are they going and doing gaming? Because they want to escape reality. They want to be part of something bigger than themselves. They want to kill zombies and save the world. Well, you know what? We have tons of really epic challenges, not just at NASA, but in every single industry that can tap into the passion or excite a student. And then once we grab them, we capture that motivation, that passion, and it's our job to feed them what they need to learn, to help them to solve those problems, and to connect them with peers or near peers in academia and in industry to show them how to solve their problem. I would have been really excited to do that if I was a kid, instead of just going in my garage and almost blowing the house up. These are failures of imagination, okay? It's also a failure of culture. How many people think NASA is a really cool place to work? Very innovative, you do lots of exciting stuff. You're totally wrong. NASA is not the same place it used to be. It's a large bureaucratic morass of rules, processes, and procedures. It needs to reinvent itself. A couple of pockets of people doing really creative stuff. To be creative, you have to be a rebel, which is why I don't know how I still have a job, but I do. And if they don't see this video, I still will, but probably not. This is what I believe. I believe kids love to solve problems. And the bigger the problems, the better. And we can get them and hook them into it. I think the environment, the culture creates whether or not we're going to be creative. We have to be able to allow kids to fail. How do they learn? Just like Chris said, they pick up something and they start doing it. It doesn't work. They keep doing it. But they're in a very safe environment. Nobody's watching them. It's psychologically safe. They can fail and it's good. And so a lot of what you see in education, the Khan Academy, you go out there, the kids take the videos at home, they watch them, they take the test, they fail, they keep doing it, and they don't get tested on it. What they do and grades, when they pass that skill, they move on. It's like the Boy Scouts and the Girl Scouts. You demonstrate that skill, you understand it, then you move on. And the teachers can go to a dashboard and watch to see where the kids are stuck. And they found out that once the kids get stuck, they can go in there and unstick the student by giving them a little assistance, could be peer-to-peer, and that kid will rapidly rise and be right up at the top of the class again, rather than getting left back. And they won't miss any pieces of knowledge that they needed to learn. Okay, if you get a 70, you pass, but you might have missed some really critical component that scaffolds into something you're going to need to know later on. So we could revolutionize the way we educate. So my passion right now is imagine a world where every kid can learn by solving real-world problems that are of extreme interest to them. It could be aerospace, it could be race cars, it could be undersea exploration, whatever it is. Every one of those problems is a multidisciplinary problem that you can decompose into all the subjects that every engineer, every scientist will need to know, and has a course in it. We can capture those courses online. These kids could go to those courses online. They should be free, and a lot of them are. And they could dive in as deep as they want. And they can get graded on it, right? And imagine if we had subject matter experts that could help mentor them when they get stuck in those areas. And then they could get rewards for that. So it's kind of like gaming, only we're solving real problems, and they're learning as they go. I'm doing this also for open innovation, because I get my ideas by going to places where people tell me I can't do something. I get motivated to prove them wrong. And those are the kinds of kids I love to work with. And kids love to do that. We shouldn't be beating them out of them that, hey, there's only one right answer. And so the problems I like to work are open-ended design problems where there are millions of answers to the problems. There's not just one right answer. And you can try things and fail and learn as you go. And so I'm using an open innovation environment, and I'll show you how we do that, to get teams of students or adults around the world to solve these problems simultaneously, and then we can harvest those ideas. We could look and cherry pick which ideas we want to continue to work on. And, this was a great era. Look at what the Apollo program did to education in our country, the graduate rates. Look at what it did to patents and innovation and how that helped our economy. That's never going to happen again. NASA's budget's always going to be flat or decreasing, unfortunately. The country isn't investing in research, but we should. And this is a national problem. NASA doesn't get it. The country doesn't get it. And we're going to be at a loss for this. So we have to figure out a way to do this for not so much money, to solve these challenges, to create these challenges, to solve them. And that's where the innovation has to happen, where we have to be creative. How do we do this in a world that is working hard to prevent you from being innovative? And I'll show you what I'm doing. And this is the part we can't tell NASA. And so one of the epic challenges we had to solve before I flew was, how do you repair it? This is the hole that happened in that wing leading edge that you didn't get to see from that test. And the people on the ground said, don't worry, it's not going to be a problem. The crew was up there, they had no clue. Now, we're going to fly, missions after us are going to fly. If we see this, how do we fix this before we fly again? So this was a cool epic challenge. I watched large companies try to solve this problem and fail. And I'm sitting there, I'm frustrated as heck, because I spent 22 years of my life as a research scientist at NASA Langley exactly on problems like this. And I was like, put me in, coach, we can do this. My boss said, okay, you can still be an astronaut, go see what you can do. Went in my friend's garage, this is Don Pettit. He's the ultimate geek astronaut. He's my good friend and classmate, been on space station several times. Has a garage that's like a laboratory, a science laboratory. We went in there and we had permission to fail because nobody knew what we were doing. We didn't tell anybody what we were doing. And we tried things and failed fast and furiously. Lots of different ideas that I could think up, that Don could think up, that our friends could think up. I had friends, the Friends of Charlie Network, around the world, because I'm an old guy, and we tried lots of different things and failed. But we were like two little kids. Like when we were back, I knock on his door, ask for permission from his wife, Mickey, could Don come out and play? We'd run to the garage, and until I actually got assigned to the flight, and then I had to start doing other things. This isn't playing, but it's a video of a drill bit that people told us was impossible to do. And this is a year and a half before our flight, and we went in the garage and we solved the problem that nobody else could solve because nobody tried chipping the coating on the material before you drill through it, which is real easy to do in space with a center punch. An astronaut goes out there in a spacesuit, chips it, and then you can drill through it. So we ended up flying, and we got patents on this in a year and a half, certified, tested for flight, 2 drill bits in case we had to drill a hole in the wing. We could tap a perfect screw size in there, in a perfect size hole, and we could fill that damaged region with a fastener and attach it. Or we could develop these plugs that we would basically use, and this is a test of one. And here is a test in an object, simulated heating that flows from left to right. You get a very high local temperature because it sticks up in the flow a little bit, traveling at Mach 25. Okay? And industry's patches were failing. They didn't know why. This is where you go to the Friends of Charlie Network. A good friend of mine, Pete Nafo from Brooklyn Poly, was working at NASA with me, and I said, Pete, is there a way we could do some analysis? This is a world-renowned computational fluid dynamics person, an aerothermodynamicist, ran the code. He said, you know what, Charlie, if you keep the thickness of the patch about 1/10 of an inch or less, the bevel angle of the patch less than 6 degrees, it won't burn up. We only had about 200 degrees margin. This thing goes up to about 3,000 degrees when we were re-entering the atmosphere. Sure enough, it worked. But it was being able to connect with just the right expert at just the right time, to know who with the know-how, bring that person in that network, and this is what we want to do with these kids. We have an expert network and adults. This is how we should solve problems. Search for that expert, bring them in at just the right time, get their input, get the answer more than likely, and then move on. So what happened was we ended up handing this idea over to industry. They did the due diligence to construct the patches. In Don's garage, we tested a design that was doubly curved and thin. It was a ceramic material. Everyone said you couldn't make it thin, but the thinner you made it, the more flexible it was, so that as you press on it, it conforms to the shape. So now, instead of us having to carry 1,800 patches, in case there was a hole in different regions of the curved wing, we only had to carry 18. 2 orders of magnitude less. And we probably wouldn't have carried any patches if we didn't step in and do that. Okay, so what do we use as engineers? We use a building block approach. Okay, you have an idea. First, you have a concept, and this is where you use your imagination to solve these problems, right? And now, as engineers, you use analytical techniques to try to predict how that concept is going to behave. You go out there and you think about all the different ways it can fail, so that now when you're doing these, and I like to call it failing smart, fast, small, cheap, early, and often. You can learn how to fail successfully and correctly. Rather than failing the people who are on the launch pad, you fail in the laboratory. That's what all researchers know how to do. Okay? And you understand the failure mechanisms, you keep scaling up, putting in more pieces, adding the complexity and the interaction until you're finally ready for a final design. Now, if you don't do this, okay, this is the X33 program. This is an actual idea we had for a reusable cryogenic tank that would store liquid hydrogen, okay? People at Lockheed didn't listen to us. We said, you know what? That honeycomb core is going to fail because hydrogen could leak in, air could leak in, liquefy because it's so cold, and then when you launch, it gets heated up, it's going to blow the honeycomb apart. They could have solved that problem right here, one of these tests, instead of going and building a full-scale tank, very complicated, very complex, very expensive. When this failed, it killed the entire program. Is that my time?
I think 5 minutes.
Okay. So this is the technique we use. We applied this. They said, Charlie, proved that this could work. We did it for young engineers trying to solve a whale landing problem, to young NASA engineers. Right now, the capsules land in the water, at least the U.S. ones. Took one of those ideas, went to students at MIT and Penn State. They went through 3 rapid cycles, like what Peter was talking about, using a spiral technique. And in 2 years, these students came up with a solution that NASA and industry could not solve. Not only did they come up with a personal airbag system that would allow the crew to land safely, but it would save mass, and you could stow it by deflating it and stowing it and add habitable volume. So imagine if we had hundreds of these teams of students solving these problems. So this is the Epic Challenge program. We're connecting, and Peter is working with us, 5 different universities, undergraduate students, a full-year capstone program. The teams are mixed teams, geographically dispersed, students from each university on these teams. So being able to collaborate and work virtually is very important. We're capitalizing on the creative ideas. We're linked from below. We're linking the undergraduates with high schools and also middle schools. We're creating the curriculum up here. The high school teachers and middle school teachers creating the curriculum and the lesson plans. So now when they create these lesson plans, they put them on Peter's platform. We share them with teachers around the world, and all the students can get connected to these problems. This is the platform Peter showed you, and when you look under groups, you'll see an Epic Challenge group, and Peter created that for us and our team. And if you click on that, you'll see some of the lessons that we developed from world-class experts. Those lessons, when you look at them, could be a video. We have a running transcript, an oral transcript. And Peter on the program has a place where the students can collaborate just on that lesson. And he was going to show you that they also have whiteboard capability. We're also teaming with Siemens Corporation and other folks so that they can visually create computer-aided design models, share those models, and annotate and make changes to those and pass them along. So we're using this as a way with students, but really, if you think about this, we're going to open this up for a massive open online project next year. We'll have thousands, hundreds of thousands of students around the world working on a very similar problem. We're going to have to scale up, and that just shows. This shows the discussions. This is using the IQ4 platform, our friend Francisco, and shows how we can now dive in and see how these students are collaborating around a given topic, the give and take, the flow of information. What you didn't see in one of Peter's charts was data analytics. We want to be able to monitor the analytics to make sure the data and the communications from different areas of expertise is happening correctly. And let me see, Peter, that's it for me. You want to wrap it up?
Sure.
Maybe show one of us?
I can probably flip to a live version of the system. And this is what it looks like. I don't want to take too much time because I think we're probably getting picked out. This is what it needs to open up the bench.
It's okay, we got time.
I'm sorry?
You got time.
You got time? Okay. All right. Let me. Sorry.
And we're following the same process that Peter mentioned. We're trying things as we go. We're changing things rapidly. We're getting feedback from the students that goes directly into the products that we're using in the platform. And we're learning from them, because they know best how to communicate. I'm a digital dinosaur. Most of these kids are way ahead of me.
So the platform basically consists of three main areas. Create, which is where you can create a lesson. Request, and this is an area that we're evolving, which is as important as the creation of lessons is what are people interested in, what do they want. So part of the contribution can be just ideas, and you can crowdsource those. And then we can browse through the different lessons and be able to do different things with them. I'll show you one. Here's some of the stuff that Charlie has in there. But I'll show you one that has an example of an embedded transcript with chapterization and chunking that is referenceable.
I'll give you an example. Peter talked about asking requests. Students are asking, well, we need lectures in this area or that area as they're trying to solve this problem. As they're diving in, trying to learn these new areas. And so they can request new lectures, for instance, and we can go out there and get those lectures for the students.
So this is a small lesson. We took the video, we transcribed it, and added chapters. And those chapters are addressable. So I can go in and say, I don't want to use that chunk. I'm going to just use this chunk. So anywhere in the system that you build these chunks, you can repurpose them and reuse them. Right, you can search through the text, you can search through metadata. Metadata is a huge problem and challenge because people don't tag well necessarily. So we're working on a lexical analyzer to basically help us auto-extract. And it's a complicated process, largely driven by dictionaries that are domain-specific, but that's one of the areas that we're doing a lot of research on, is trying to figure out how do we aid the process of getting the metadata, which then can be used to abstract out to the bigger chunks, to the chapters.
So if you can imagine a repository with all this content that's now searchable, each individual professor could basically pick and choose the sections they want to use and customize their lectures accordingly. And another aspect we're looking at is automatically linking what the lessons and the outcomes are expected from that lesson to ABIT criteria or different standards, next generation science standards for high schools and local regions to help the teachers and the educators to make their job a little bit easier because no one wants to do that.
We also track behaviors and award points, and we can actually give badges and certificates, and we're integrating some gaming technologies, all of which can be done relatively easily, relatively quickly by virtue of the platform and its modularity. That's one of the core principles, is if we had to build this all in a big bundle of code, we'd never get this far. We would not have gotten this far in 6 months, and any new additions would take more and more time as the system gets bigger. So this helps us control the rate of change or the cost of change to help us innovate. And that's basically the good ending for our talk, I guess. Any questions?